Everyone.
Hello, how are you?
Good. Welcome to our second lesson after the one that we did last week. Last week, I'm sure all of you will agree, it was very general. We're trying to introduce mathematics at our level now, grade 10, grade 11, grade 12. It was very general. We talked about numbers. We talked about Petit and Mohini. Actually ended up with some idea of what a function should be like. We saw variables, we saw an independent variable, we saw a dependent one, we saw what we call a domain or the domain, we saw the range, we saw roughly how to make a graph. You remember? Yes. And of course, in terms of numbers, we talked generally. We talked about counting numbers, we talked about odd. And we said counting numbers are actually what we know is natural numbers. We talked about negative numbers. We talked about fractional numbers. And we said, of course, there are many other numbers, like real numbers. We've got irrational numbers. We've got rational numbers. We'll talk about those later. The logical thing for us to do now is a topic that I'm going to introduce today. Sequences and series. This is a grade 10, grade 11, grade 12 topic in your syllabus. And we will talk about this topic from that level, grade 10, very basic, build it up to grade 11 level, build it up to grade 12 level in this lesson. Okay? And as I said to you last week, or in our previous lesson, we will have lessons where we are teaching like now. Then we will also do tutorials where we actually look at problems, practical examples, exam questions, past exam papers, apply the principles that we learn herein to solve those. That's what we'll do. Anyway, let's start. If you remember what we said last week, when we are counting, right? Nobody wanted to be counted as 0. Nobody wanted to be counted as 1.5. We saw that we count from 1. We add another 1, we go to 2. We add another 1, we go to 3. We add another 1, we go to 4. And we can continue like that. If you can see, there's actually a pattern there. It's very systematic. If I tell you, okay, start counting from 5, naturally, you tell me, okay, fine, 5. The next thing that's supposed to come is 6. And if we're at 10, what will come next? 11. We all agree.
Yes.
So if I were to write our very simple numbers in the way that we actually count every day. 1, 2, 3, 4, 5. Agree? What comes next?
6.
What comes next?
7.
If I am now at 100, what comes after? 101. Correct. That's good. That actually is a very good example of a basic sequence. It's sequential in nature. We can see what comes after. We've got a simple pattern here, which is very easy to look at. And that's what I actually want us to discuss, and then we expand that concept, that principle. Happy? Okay? I can see immediately, if I want to move from one number to the next number, going forward, that is, going to the right, what am I doing? I'm adding 1. Then I get the next number. If I want to move further, I add another 1. Then I get the next number. Okay? In this special case of counting numbers that we're talking about now, I can also see that my starting number, what is my first number? 1. Are we all clear with that? Okay, good. So, we'll write this, the starting number. Alright? Let's call it for now the starting number. Or we can alternatively call it the first number. That should be very easy. That's pretty logical. We're starting with 1. From there we go to 2. Then we go to 3. We add 1, we go to 4. We add 1, we go to 5. And we can continue like that. Are we happy? Good. Second thing, we can also generally talk about what we are seeing there. All these numbers, as we see them, as terms. So I'm going to write that down. Terms of that sequence which I've actually introduced. All right? So, I can come and say, this is my first term. That one. 1. Then obviously, 2 becomes my second term. 3 becomes my third term. 4 becomes my fourth term. 5 becomes my fifth term. Are we happy?
Yeah.
Good. Now, as I said to you last week, when we were talking about fish, we were talking about apples. We said normally, we don't necessarily have to be writing all those things like fish, apples. We can actually find letters to represent whatever that we want. For example, we ended up saying fish, let's actually represent that with F. Apples, let's actually use A. We can do exactly the same. So, I'm going to write that, in fact, our terms, instead of always writing term 1, term 2, term 3, term 4, let's actually decide to represent our terms with the letter T. Alright? Good. If we do that, then how then are we going to know which term or what term we actually represent? We are going to use a subscript on the letter in the following manner. If this is going to be our first term, let us agree to call it term 1, T1. Which means that we can then go on to call our second term, which is 2 in this case, T what?
T2.
T2. Our third term,
T3.
T3. Our fifth term,
T5.
our 100th term,
T100.
T100. Let's suppose in general, we continue until we come to some term, which we don't know at the moment. We can actually call it our nth term. Come to n terms. We've got a total of n terms around. So we can call that in general Tn. Any other term that we can think of, we can find it. And we'll see that just now. So let's call that the nth term, Tn, represented like that. In general. Are we happy with that so far? Good. Now, because we have said that we've got a first term, a starting term, it's a very important term that we need to know where we are starting with our sequence. For example, I can actually choose not to start with 1. Say in one particular case, I still want to look at a very similar sequence, but I actually want to start with 3. It means therefore that my T1 for that particular set of numbers or sequence will be 3. That will be my first step. Do you agree? Yes. I can, for example, say I actually don't want to start that side. I want to start my sequence at 100. So from there I've got 101, 102, 103. My first term in that particular case will be, instead of this being T100, it now becomes T1. 101 becomes T2, 102 becomes T3, and so on. Happy? Everyone so far? And are we taking notes? Maybe nothing much to write about at the moment. It's still very easy. Good. Now, we've got a special way of representing our first term. We are going to use, let's agree, to use the first letter of the alphabet. First term. Let's use A. So our T1, let's represent it with the letter A for all cases that we're going to work with. So whenever we are going to see that later, when we're dealing with sequences and series, as you see just now, we know it actually represents our first term. That's the starting point, the starting line. Right? Understandable? Then, let's also say the following. Because we will not necessarily want to restrict ourselves to the terms that we can count, like maybe 1, 2, 3, 4, 5. We can talk of the 1,000th term, the 1,000,000th term, or in general we say the nth term. Okay? So, we can follow each and every one of these terms until we come to Tn if we want. How can we do that? If we look at T1, our subscript n, which is the general one, in this case, will be 1. That's our subscript. Our subscript in this case will be 2, so n is actually equal to 2. Our subscript, this is our third term, T3, our subscript is 3, so our n is equal to 3. Of course, when we come to the nth term, our n is actually equal to n. Is that a bit more difficult? Now? It actually isn't. You see that. Just now. It should be very easy. Right? That's good. Now, what does it mean? We are saying we are starting with the first term, T1. The subscript of that T is 1. The second term, T2, this 2 is our n. So our n is equal to 2 here, our n is equal to 3 here, our n is equal to 5 there, our n is equal to 100. Now I want us to ask ourselves a very simple question. If we look at, in terms of the terms, obviously we are moving from the first term to the second term to the third term to the fourth term, and you can see again, similar to this sequence that we have here, we are actually adding our terms. We actually add 1 every time we want to move forward. So obviously, if I talk of term 1, in any case, if you try to look at it, we are talking of counting numbers here. I wouldn't want to talk of, this is my term minus 1. I'll start counting at 1, like what we say with natural numbers in the previous lesson. So I'll start, okay, this is my first term, second term, and as I move forward, from 2, I add 1 and I get 3. I've got 3 now. To come to the following term is obviously this plus 1, we come to 4. To move to that is that plus 1, we come to 5. So we're actually adding 1 as we continue. As we continue counting our terms. Now I want to ask you a question. If we talk of a term in general, any term, right? There are 2 things that I actually want to hear from you. Obviously there is a term before this one. Just like there's a term before before this 5, this T5, the term is 4, or T4, n equal to 4. Before 4 we've got T3. What comes just before Tn? Say it out.
Tn minus 1.
Tn minus 1. Great stuff. What does that mean? I know this might actually sound abstract. It's not. What are we saying? We are saying if we have got, say, T20, the 20th term, what is the term before that? The term before that is T20 minus 1, which is actually T, which is the same as T19. That's all we are saying. Is that understandable? So that's what we mean by n minus 1. So obviously, if I were to ask you again, Petty, I do agree with you that the term before that Tn, in fact, let's rewrite it this way. In general then, if we talk of a Tn, an nth term, Petty has said that just before that, the term before that, because remember it's always additions of 1 going forward, should be Tn minus 1. Can I ask another question? What is the term therefore just before Tn minus 1? What do you think?
Tn minus 2.
Tn minus 2. How do we know? We are saying, in all cases, for us to move backwards, we need to subtract 1. So in this case, if you're going to be moving from Tn minus 1, we are going to end up with n minus 1, which is n minus 2. So we actually end up with Tn minus 2. Question. What is the term after Tn? After, to the right. Patsy?
Tn plus 1.
Tn plus 1. Because we are going to the right, just like what we saw with our number line. We go to the right, we add. We go to the left, we subtract something. In this case, we are having additions of 1 at a time for us to move from one term to the next term. Isn't it? So obviously the term after Tn plus 1 will be Tn plus 2. And so on and so on. Do you agree with that? Does that still sound sensible? We're not speaking Greek at the moment. It's still very basic, isn't it? Very easy. Good. At least I'm happy that we all understand at the moment. Enya, are you okay with that? So far? Good. We say cell phones off already. The first thing is, we have seen, we are going to start somewhere. We are going to have a first term, which we have actually agreed to call A, all the time. Right? We have agreed that we can actually look at the members of our sequence as terms. And obviously, because we are going to be counting something, we are going to use natural numbers. We'll count naturally from 1, next 2, next 3, and so on, which is exactly what you're doing. So our first term is effectively, this A is actually T1. Then we go to T2, then we go to T3. Tn minus 3, Tn minus 2, Tn minus 1, Tn plus 1. And we continue like that. Happy? Good. I am happy that you guys are actually understanding, which is nice. So we'll try to keep it very simple, but we'll cover everything that's required of you in your syllabus. In a very simple way. And we'll derive everything. So again, like what we said last week, no formula books in here, no calculators in here, we'll use our heads. And we'll see how easy and basic all these things are. Okay, including all those things. I mean, I know people like Mohini, you've probably seen those big formulas or whatever. We'll see how to get them very easily, very basic. And that's what I actually want to empower you with. To be able to derive these things from very basic considerations on your own. Okay? Good. Now, let us examine our natural numbers again. I'm going to give you a definition now of what a sequence is. Still here, we are going to see that there's actually quite several or different sequences, different types of sequences that we're going to actually talk about. Okay? The only thing, or the whole idea is that when we talk of a sequence, we are talking of some systematic numbers put together, which we can easily follow. We can find a way of describing. If I were to give you 2, 3, or 4 terms, you should be able on your own to continue the sequence. That pattern. So it's essentially a pattern. What is a pattern? A pattern is obviously something which is systematic. It's not disordered. It's not disorderly in nature. Let's look at the following. If I were to have this 1, 2, 3, 4, 0, 7, 200, and I ask you to continue with that pattern, do you think you can? You can't. Not at all. It's just impossible. It's not systematic. In this case, it was easy because we could see what this person is doing. To move to the next term, they're essentially adding 1. And they get the next term. And it's consistent throughout. So we have a pattern. In this case, let's look at this guy. When I look at the first 4 terms, remember this becomes our T1 or A, this becomes T2, this becomes T3, this becomes T4 in this case. Alright? The problem with this is, yes, it looks like we do have a pattern initially. He's adding 1, he's adding 1, he's adding 1. All of a sudden, we don't know what he's done here. Is he subtracted 4? Is he multiplied by 0? Then what has happened here? Is he added 7? Maybe. We don't know. And from there to there, no idea. So it's not systematic. Now, let us look at a proper sequence, like the one that we actually have been having on the board. Our own counting numbers. It's obviously a sequence. It's a pattern. Alright? It is. Let us look at what we have here and define a few things which will be very much applicable to every other sequence that we actually look at. We'll look at probably 5 or so examples now, apart from this basic one. We'll talk about the number the times tables that we used to play with. During my time, back then, we used to have these exercise books, which you go to the next side, 3 times 1, up to probably 3 times 20, etc., etc. All those examples of sequences, right? We'll see examples of that here, just about now. Let us look at the natural numbers as a sequence. Okay? Obviously, as we've agreed, this is our first term. What are we doing to get the next term after that? Can someone give us an answer? What do we do?
Add 1.
We add 1. After that, we add another 1. After that, we add another 1. And we continue like that. Easy. Right. Let us also look at something here. There is something which is common. Whenever we look at a pair of terms, neighbors, like Tn minus 1 and Tn, or T1 and T2 as an example, T5 and T6 as an example, T100 and T101 as an example, there is something which is common. Every pair of neighbors, if we look at their difference, it's fixed, it's a constant. For example, if I were to look at T2 and T3, right? And then I look at T4, and then I look at T5, there is something which is actually common with all those terms. For example, if I look at my third term, and I subtract my second term, the term just before it, so T3 minus T2, I'll get 1 in this case, 3 minus 2. If I do exactly the same thing, T4 minus T3, the term minus the term just before it, I get 1 again. If I do the same thing, T5 minus T4, I get 1 again. 5 minus 4, 1. Obviously now, I can tell you that if I come here, this is my 100th term. I don't necessarily need to think about it. I have seen that is actually consistent. I can equally tell you that T100 minus T99, the 99th term, should be equal to 1. Good. As well. So, what about in general then? If I have got an nth term minus the term just before it, which is Tn minus 1, what would that be in this case? 1. Good. Correct. Happy? Everyone happy? So, we have seen that we have got a common difference. The difference between neighboring terms is always common. It's always a constant in this particular case. So let us introduce a slightly new concept regarding this sequence that we're actually looking at the moment. We have seen one. We have got a first term which we've actually decided to call A. Right? We have seen that we have got terms T1, T2, T3, T4. We have now just seen that in general, neighboring terms Tn minus Tn minus 1, that difference in this case, which is 1 in this particular case, is actually common. Let's call it a common difference. Okay? It's common everywhere. Once I take a pair, subtract the smaller or the previous term from a term. If I've got Tn, then I subtract some tn minus 1, that difference is common. In this case, it's 1. Right? Common difference. To simplify, just like what we've actually been doing with everything else we've dealt with up to now, common difference. Difference. Let's actually decide to call this common difference D. So when you see the letter D, in this case, that represents, or that means our common difference. One term minus the term before it, in this particular case, will give you a common difference D. In this case, our common difference D is equal to 1. Because every time we subtract a term from the term after it, we get 1. D. Right? So we've just introduced something else. Common is equal to D, the common difference. Second parameter that we actually talk about whenever we talk about sequences. Everyone still happy? Yes. Ah, great, guys. That's good. That's very good. Now I want us to take a look at something. We now want to move a step further, become cleverer, and ask ourselves, in general, can we, now having this common difference, now that we know that there is something that we are always doing, something constant that we do to one term for us to get the next term. If we are given a first term, a starting part of the sequence, and we are told of this common difference, can we then populate the whole sequence with terms just by using these two? That's what we want to see. Now, if you remember what we said earlier, can I take this off now? Okay, if you remember what we said earlier, we said we can actually look at this as terms. T1, T2, T3, T4, T5, T100. Of course, we have got T6, T7, T8, but we cannot continue writing them. It's not necessary. T100, some Tn minus 1, some Tn plus 2, or Tn plus 1 in that case. Sorry, I mean in this case, then Tn plus 2, and we continue in that order. Right? And we also say, this we can represent with the letter A. Happy? And we also say, if we look at this subscript, M in general, this is our first term, so our subscript is actually 1. Second term subscript 2, and 2, 3, 4, 5, 100, n minus 1, n, nth term. Right? Happy? Good. I want to ask now. Let's suppose somebody just tells us, you know what? For you to make up the sequence that I'm going to give you here, I've got this sequence in my bag, in my secret bag. I want you to tell me the terms of that sequence. This is the information that I'm actually going to give you. Right? My starting term of that sequence in my hidden bag is 1. My next term is 2. My next term is 3. My next term is 4. After that it's 5. Can you please continue with the sequence and tell me, and I've got plenty of those terms in this bag. Can you at least give me the first 100? Obviously we can, isn't it? How are we going to actually do that? We say, okay, fine. You have said to us your first term T1 is equal to A, which is equal to 1. Happy? And your second term is 2. Your third term is 3. I can see that to get the next term you're always adding 1. So our common difference, D, is equal to 1. Right? So, if you're going to give me a first term 1, for me to get the next term, I'll need to add that common difference. Sorry. So if I start with 1, which is your A, for me to get the next term, I'll need to add that common difference, which is 1. In this case, 1 plus 1, and you get 2. After I've got this, I'll need to add 1, and I get 3. In fact, even more importantly, if I were to try to think of it in a much more general way, I would say the following. I don't really care what kind of a sequence you are having in your bag. I can tell you in general. Right? You have just told me that you've got a first term A. And for you to get the second term, you have to add that common difference. The difference between the first term and the second term, which is D. Are we happy? Okay? If I want to get the third term, you say, you actually need to add 2 D's, because after all, T3 minus T2 is going to be D again. And that's what I'm really supposed to add. So, I'm supposed to have this term plus another D. So I can actually maintain my A, which I know already, and I end up with that, which is 2D. If we were to continue to go to T4, what do you think our term will be here? A plus?
4D.
No?
3D.
3D. If we come here, A plus?
4D.
4D. Happy? Now let's ask ourselves a very important question. A very important question, everyone. Let us think about something. Can you see that we can actually relate the D's that we're adding? We can actually relate the D's that we are adding to the term number, to this, which is this N. Can you see that? Let's look at this pattern again. Yes, you see that just now. All right? This, remember, we say that when you write a number, for example, if I want to write A or 2, 2 is the same as 1 times 2. So we are always silent about the 1, which multiplies numbers. So this is the same as A plus 1D. It's correct, right? A plus D is exactly the same as A plus 1D. Only 1D. Correct? Then we come to plus 2D, plus 3D, plus 4D, and we continue. Let's take a look. If this is our first term, this one, T1, what's happening here? We don't know yet. Let's look at the next term. If this is our second term, so when n equal to 2, we are having 1D. When n equal to 3, third term, we are having 2D. When n equal to 4, we are having 3D. Our A is constant throughout, as you can see. When we are having n equal to 5, which is the fifth term T5, we have 4D. Now, let's ask ourselves a question. What about when we have, in general, an nth term? How do we know what that term is going to mean? How do we know the term? Obviously, as you have seen, our A is maintained throughout. So we can confidently write that yes, we're going to have the first term plus something. You can also see that our D is maintained throughout plus something that we don't know for now times our D, which we have seen already. And we have just seen this pattern. N equal to 2, we have 1. 3, 2. 4, 3. 5, 4. In general, n minus 1. Good. You can see that what we are multiplying our D with is always the term number minus 1. It's 2 here, we are multiplying by 1. It's 3 here, we are multiplying by 2, which is 3 minus 1. It's 4 here, we are multiplying by 3, which is 4 minus 1. If it's n, therefore, that's what we have. That's easy, isn't it? Yes. Pezzi, does that make sense?
Yeah,
It does?
yeah.
Good. So what have we just done here? What we've done here is to represent the terms of this sequence in general. Are we happy? We have. Because we are saying that, let's take a look at this again. T1 is equal to A. That should make sense. After all, we have said that the first term T1, we call it A. So that makes sense. The second term T2, we are saying is equal to A plus D. A plus or common difference, A plus 1D. That's our second term. Our third term, A plus 2D. And we continue. Our nth term, Tn, is equal to A plus n minus 1D in general. So we can remove all that now. All this. And this is what we are looking for. And we have seen how to get it. Tn, the nth term, any term, is A plus n minus 1D for this sequence. Happy? I know it might actually sound a bit hectic for you, seeing it probably some for the first time, but it actually means nothing. Let us see how we can actually use that. Alright? Let's see. What does it mean? Can we make sense out of it? Let's go on to say, okay, here is our sequence again. Natural numbers, counting numbers. We have agreed this is the first term. This is the second term. This is the third term. This is the fourth term. Fifth. This is the 100th term. Right? If we try to look at it, what term is that? What term number is that? N. This is 1. We can see that. This is 2. This is 3. Third term. Fourth term. Fifth term. 100th term. So n equal to 1 here as we start. N equal to 2 here. N equal to 3 here. N equal to 4 here. N equal to 100. Simply means the 100th term. Okay? Or T100. Now let's look at our relationship between the nth term, the first term, the common difference, those three parameters, and relate that to this sequence as we have it here. Something that we know. We know that our first term, t equal to 1. So if you want to find t1 as an example, what is t1? It's the first term. But what did we say? The first term is A. So if we are right, this should actually give us A. Because we know that T1 is equal to A. So what does it mean? If we want to use this to find our first term as an example, we'll say, okay, fine. The first term is T1. What does that mean? It means that N equal to 1. To Tn, T1. So N equal to 1. What does that mean? It means that T1 is equal to A, which we don't know, plus N, but what is N? 1. We can see that. 1 minus 1 times D. What does that mean? It means that T1 is equal to A, 1 minus 1, plus 0D. Obviously, something multiplied by 0 will give you 0. We can see this is equal to A. Correct? And for sure, T1 is our first term. It's A. Are we happy? Good. We know that in this particular case, of course, we know that A is equal to 1. So our first term in this particular case is 1. If you want to find T100, say, as an example, we know in this sequence, our 100th term is 100. Can we use that relationship to find the 100th term? We say, okay, fine. T100, we know that Tn is equal to A plus n minus 1 D. Now, if someone comes and says, now, find your T100 for this sequence, you say, okay, fine, cool. If you want me to find T100, I can see that. What is n now? N equal to 100. Good, guys. What is A again? What is A equal to for this sequence? Ah, you're not active. What is it? 1. Good. What is the common difference of this sequence? I mean, in this sequence, we have seen that the difference between two terms, neighboring terms, in this sequence is always 1. If here, T2 minus T1, 1. T3 minus T2, 1. T4 minus T3, 1. T5 minus T4, 1. And we are saying, remember, by definition, we say our D represents our common difference. Tn minus 1. So we also know that D is equal to 1. Correct? So, if we are correct about this relationship, we should be able to find T100. And we know that T100 is actually 100. So, a not very clever person like yourself, if they didn't ask to find T100, to find the 100th term, they would actually probably get a big page, start writing 1, 2, 3, 4, 5, 6, 7, probably right up to about 200. Then they probably go back and start counting 1, 2, 3, 4. Therefore, now I'm at T100. That is my 100. So it's actually 100. But then we will not do that. So let's try to find our 100th term using that. It's A plus n minus 1d. We know that n is equal to 100 in this case. We know that A is equal to 1. We know that D is equal to 1. So it's very easy. A1 plus 100, which is our n, minus 1, multiplied by our common difference, 1. This will be equal to 1 plus, what is 100 minus 1? 99 times 1. This is the same as 1 plus, which is equal to 100. So do we agree, therefore, that we can still find our 100th term by simply looking at the sequence that we saw, which gave us that relationship that if we are given such a sequence, the nth term is always your first term, number of terms minus 1, which is n minus 1, times the common difference, d. Let's take that down, because you need that. I know in your formula books you always be given that, but we don't want to see you going to look for that. We want you to understand it. I think you'll agree with me. It was very easy for us to find this relationship. Tn is equal to A plus n minus 1d, just by looking at the pattern. So why should you be so much shortchanged by somebody just coming and giving you, okay, you know what, claim this. Why should you? It's not necessary. We can get it one-on-one. Now, our sequence, I'm sure you'll agree with me, is a very simple sequence. And let's actually go on to define something very important. A sequence like this one, where we get the next term simply because there is something constant that we're adding. We have seen here, we were constantly adding 1. Right? Such a sequence, where we are simply having a common difference, and we have to simply add that common difference for us to find the next term, is called an arithmetic sequence. So sequences where terms have a common difference D in general are known as arithmetic sequences. Arithmetics. A long time ago, people in schools never really used to do the mathematics that we do now. They actually used to do some arithmetics, addition, subtraction, basic stuff. I'm sure it's actually the same thing with people who do math literacy. More of arithmetics. Add this, subtract that, basic stuff. Essentially, that's what we're doing here. Add something, a fixed something, to get the next thing. And what is the sequence after all? We've said it's actually a pattern where we can logically say, okay, fine. for us to get the next term, what are we doing? There's something which is fixed that we're actually doing. Right? We can represent a sequence simply as 1, 2, 3, 4, 5. Or 2, 4, 6, 8, 10. We can put commas. We can put such to represent the different terms. I want you to understand, upfront, that if I were to come up with an operation of some sort, say I choose now, that okay, I've seen the sequence, but I don't want to do that. I don't want a simple sequence anymore. I choose, for example, that instead of just looking at that as a simple sequence, I actually want you to be adding the terms. As an example, once we start having an operation such as adding terms or subtracting terms, it's not a sequence anymore. We call that a series. So that's actually the only difference between a sequence and a series. In both cases, we have a systematic way of finding the next term. However, with a sequence, we are not having an operation. The terms are independent in terms of we are not trying to add them to each other or subtract or whatever operation we can think of. It's just term after term, and we are just looking at a very simple number pattern, number or sequence of numbers. When we start adding, subtracting, we are now talking of a series. We are not talking of series now. We'll talk of series probably in the next 30 minutes. But just as much as we said, this sequence without the additions is actually an arithmetic sequence because we are adding a common number. Or maybe we could be subtracting a common number, but there's that common difference. Equally, if we were to look at a series where the terms are also simply separated or simply dependent on each other because of a common difference, we call such series an arithmetic series. We can also call it an arithmetic progression. We progress arithmetically. Okay? Enough of talking about series for now. We just wanted to mention that it's probably another another sequence, very similar, but probably slightly different. Okay? Let's look at this one. You remember like the times tables that I was actually talking about? Okay, let's not even talk of times tables. Let's say we want to count in twos. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, etc. and so on and so on. This is what we'll do. We can agree. Where do you want to start? I'll say probably let's start at 2. So, say okay, there's our sequence. 2, 4, 6, 8, 10, and so on. Correct? I'm going to ask you questions and you give me the answers. Does that look like a sequence to you? Is it orderly? If I were to ask you the term to find the term after 10, can you find it? What is the term?
12.
We're all agreeable. It's 12. So this is actually an example of a good pattern. It's not like the other one that we saw, where all of a sudden we basically lost order. So this is a pretty systematic way of writing the steps. So it's actually a sequence. Now the next thing for us is to find out what type of a sequence is it, or rather it is. I know at the moment we don't know any other type apart from the arithmetic one that we've actually dealt with. But let's just confirm that it is. Right? We've introduced in the previous 30 minutes or so a few aspects, a few parameters that we can actually use to describe sequences. We said we always have a first term, which we call, in general, A. Is everyone happy with that? So if I would ask you, What is our first term? What is A for this sequence? 2. Good. Now the next thing that we need to investigate is D. Do we have a common difference? For sure. Right? Yes. We need to find that. How do we find that? We say that the common difference is always found by that should always be equal to D if it is an arithmetic sequence. Right? So we are going to take several pairs, right, and check if for sure we actually having a common difference D. So we can start. Let's probably start with this one. What will be this term? T2. This one is T2. It's the second term. So if we want to find the common difference using this term and its predecessor, we'll say, okay, T2 minus T1. Obviously, this is T1. What is it equal to? It's 4 minus 2, which is equal to 2. If for sure we're having a common difference, then if we take any other pair and do exactly the same operation as we've done here, we should be able to get the same 2. So let's look for another pair. Let's take T3 minus what? T2. Good. What is that equal to? Now you have to say.
2.
Give me the numbers first. What minus what?
6 minus 4.
6 minus 4. That's equal to? So far we look fine. So far it looks like it's working. Let's take another pair. This is T5, right? So it will be T5 minus T4. What is that equal to? 10 minus 8, which is equal to? So yes, I'm sure now we agreed, we are convinced. We're actually looking at an arithmetic sequence. And our arithmetic sequence is such that our first term is 2. Our common difference is 2. Are we happy? Right. Let us go on to say, let's look at the terms. Let's now number our terms. Let's now name our terms. Obviously, when you're going to start counting the terms, we are now counting. We use natural numbers. We use counting numbers. So we are going to say, this is T1, this is T2, this is T3, this is T4, this is T5, and so on. Okay? If we try to talk of a general nth term or just in general n, we are saying T1, or n equal to 1 here, T2, n equal to 2 there, T3, n equal to 3, and we continue. Now I want to ask you, if somebody were to come to you and say, give us the 25th term of this sequence, how would we find 25th term? What is that? The first thing that comes into your head is 25th term. How do we represent that? T what? T25. 25th term. So if it is T25, what is n equal to? 25. Remember, n is always the substitute. Always the number of the term. So n equal to 25. So if I want to find T25, what do? I know that in general, for a sequence, arithmetic in nature, my nth term is always Tn is equal to a plus n minus 1 d. So now somebody comes and says find T25. N equal to 25. We can see that. Our first term is 2. So this will be equal to a, which is 2, plus 25 minus 1 by common difference. What is our common difference? 2. So this will be the same as 2 plus 24 times 2. This will be the same as 2 plus 48, which is, so T25 is equal to 50. So what does that mean? It means that if we were to continue, because this is just our probably maiden lesson in terms of sequences, let us convince ourselves that what we are saying is correct. Okay? Let's continue. If we were to continue with this sequence, we'll get 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, and so on. Now already, look at this poor student. He wants to find the 25th term, and he has to be writing 2, 4, 6, 8, 10, all the way up to 50. Let's try to check. Let's count. Is 50 for sure our 25th term? How do we check? Let's count. This is our first term. So, term 1, term 2, term 3, term 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 50. The cleverer student will say, no, I will not be writing that. Okay, say the poor student says, okay, fine, but I can get it that way. Then let's say to him, okay, fine. Since you can get it that way, let's do the following. Please find T5000. Tell us the 5,000th term. So this poor guy is going to spend the whole day, I'm sure, writing down all those terms, one by one. Of course, eventually he's going to get it. But what about you? In 2 minutes, you've actually got this thing. T5000, what does that mean? We know that Tn, in this case, is A plus n minus 1 of D. So obviously, if I want T5000, what does that mean? N equal to 5,000. But we know that D is equal to 2. A is equal to 2. So T5000 will be equal to A, which is 2, plus 5,000 minus 1 times D. This will be equal to 2 plus, what is 5,000 minus 1? 4,999. Plus 4,999 times 2. What is 4,999 times 2? It's actually equal to 9,998. Correct? Yes. It's the same as 5,000 times 2, which is 10,000, minus 2. Then plus our A. So our 5,000th term is 10,000. So if we were to count all the way to 5,000 terms, we will actually notice that T5000 is equal to 10,000. It's easy in this case. Correct? However, we don't necessarily need to continue just writing everything like A plus n minus 1D. Our A has been given already. Our D, we know it already. So for a particular sequence, we can actually write a general term. So let's take a look at this one. If we want to define our nth term in general, Tn, what is Tn equal to? We know A, we know D. How do we do that? What is A equal to? Plus, we don't know n. We are saying in general, what is the nth term? N minus 1. What is D? 2. So this is going to give us 2, n minus 1 times 2. That's very basic. We know that from grade 6 to from grade 8 or something. This is the same as 2n minus 2. So this is the same as 2 plus 2n minus 2. And we can see that 2 minus 2 is going to give you a 0. So you're going to be left with 2n. So in general, for this sequence, Tn is equal to 2n. And I think now you should actually be able to see that very clearly, because as an example, we said T25 is equal to 50. T5000 is equal to 10,000. So if I were to ask you now, what is the 20,000th term? It's 40,000. Do you agree? It's that n times 2. What is our 66th term? What is it? 1 132 is 66 times 2. Correct? Good. So we can easily write the general term, in this case, as 2n. Okay? Finally, let us look at probably a slightly different sequence, but exactly the same thing. And see if we can actually manipulate it in exactly the same manner that we've done with the first two that we've actually looked at. Okay, here's our sequence. 0, minus 6, minus 12, minus 18, minus 24. Okay, let us investigate that using exactly the same principles that we've actually done or that we've used for the other two. Like with any other sequence, we know that a sequence starts with the first step. We start somewhere. Right? So we are going to check that. And my question to you is very basic. Do you think that is a sequence? Look at it, guys, and tell me, does that look like a sequence to you? No, answer me. Does it look like a sequence? Yes, Betty?
Yes, it does.
Yes, it does look like a sequence. Good. What is our first term? Obviously, if it's a sequence, then we do have a first term. What is our first term here?
0.
A equal to 0. I'll tell you up front, it's an arithmetic sequence. So what we need to do is to find that common difference, D. How do we find the common difference again in general? How do we find the common difference in general? Yes?
It's the number in front minus the... Okay, it's T2 minus T1. Okay, it's Tn minus Tn
Minus 1. The number in front minus its predecessor. Or the number, a term, minus the term before it. So let's take a look. A good practice, whenever you come across a sequence, you don't just come and say, okay, here's a pair, let me subtract the two, and then I get a number and say, okay, this is my common difference. You will notice that with a number there are so many sequences which are actually not arithmetic, where you probably get the first 2 or 3 terms giving you a common difference, and the rest actually don't. We'll see that just now. It's very possible. So it's always prudent, it's always good to first and foremost, fine, I do agree, I might actually get a common difference, but check with several terms. Normally, let's work with at least 3 pairs. Once we are satisfied, then yes, we can move on. And don't make your pairs very close to each other. Unless, of course, the sequence that you've actually been given has got very few terms. Then yes, you've got no choice. But suppose somebody had actually had given you this up to say 36. I would now probably take this. The first pair may be from this end, maybe pick up a pair somewhere in the middle, maybe pick up 2 or so pairs at the end and confirm that for sure I do have a common difference D. Correct? Okay, so now let us try to find our common difference. Petty has just said that our common difference D is always Tn minus 1. Correct? Good. If that is the case, let us think. Let's use our first pair. What is T here?
T2.
T2 here. T1 here. T4, T5. Correct? Now, let us probably use the first pair. So, that will be T2 minus T1, which is equal to minus 6 minus 0, which is equal to minus 6. Correct. Let us look for another pair. We can take, for example, T3 and T2. So, if for sure we're having a common difference, then T3 minus T2 should be equal to the same minus 6. But in this case, we'll see, okay, T3 is minus 12 minus what? Minus 6. So it's minus because our term here is not 6, it's actually minus 6. So minus 6. We can see obviously minus minus, that will give you a plus. So we have minus 12 plus 6, which is equal to minus 6. To be prudent, let's actually do one more. So T5 minus T4. If you want, T5 minus T4, what is that? It's what minus what? Minus 24 minus 18. Obviously minus minus, that's going to give you a plus. So we are now having minus 24 plus 18 minus 6. So we are agreeable, therefore, that our common difference in this particular case is minus 6. So we can now write that. We now have that parameter. I can wrap this right. We now have that parameter D, common difference. D is equal to minus 6. What does that mean? By virtue of you having a common difference, we are saying you've got an arithmetic sequence. That's number one. Two, we are saying that you're going to start with a term, A, in this case it's 0. Then for you to get every other term after that, all you have to do is to add this minus 6. Or effectively, we are simply saying subtract 6 and you get your next term. So let's take a look at the sequence again. We start with 0. We subtract 6, we get minus 6. We subtract 6, we get minus 12. We subtract 6, we get minus 18. We subtract 6, we get minus 24. And we can continue. Happy? So far, so easy. Very basic. Good. Now, as we have actually been doing with the other sequences that we've actually worked with, it's always very prudent to have an idea of our n. We say n is always the subscript on your term. So here, if we're going to write n, in this case, for this term is 1, 2, 3, 4, 5, etc. And because we've just established that this is actually an arithmetic sequence, the same general relationship that we derived together applies, which is why it's very important for us to get things from first principles, because we can use them irrespective. We can always use them for as long as we're sure that what we're working with is exactly in the category of what it's exactly the same thing as what we actually used to derive what we want to be using here. Then of course we'll be confident. We will be. It's totally different from someone simply being told that here's a formula, use it. We have derived our own formula here. We've derived our own relationship. We know that it's actually limited to arithmetic sequences. And we know that because this is an arithmetic sequence, our relationship is actually applicable. So, what is that relationship again? What is the nth term in general? Tn? Someone? A?
Plus n minus 1.
Plus n minus 1?
Times d.
Times d. Correct? Now, let us try to, for this particular sequence, let us find the nth term, peculiar, unique to the sequence. How do we do that? It's easy. This is the general one. But because we already have A defined, we know it. We also have D, we found it. So it means that we can simplify this and make it specific to our sequence. Okay, so we can rewrite our nth term in this case, Tn, is equal to, what is A? 0 plus n minus 1, we don't know n, times D, what is D? Minus 6. Let's continue with that. This means that this is equal to 0 plus, you will notice, this is exactly the same thing as minus 6 times n minus 1. Correct? To expand this bracket, this will be minus 6 times n, which is minus 6n, minus 6 times minus 1, which will be plus 1. Sorry, plus 6. Correct? Thank you for that. Which means this is actually the same as 6 minus 6n in general. It's exactly the same. It doesn't matter the order of addition. 6 minus 6. Tn is equal to 6 minus 6n for this sequence. Let us take a few examples. Let us take a few terms and try to check if we are actually correct. Easy. Let's start with the first step. Let's see if T1 is for sure equal to 0. So T1, what is n equal to if we talk of T1? Guys, why are you quiet? What is n equal to? What is n equal to when we talk of T1? 1. So this will be the same as 6 minus 6 times 1, because n is equal to 1, which is the same as 6 minus 6, which is equal to 0. Do we agree that our first term is 0?
Yes.
Yes, we should. It is. Let us take another term. Let's take T for fourth term. T. We know that in general, Tn in this case is 6 minus 6n. So T4, my question to you guys, what is n equal to now? 4. Tn, T4, n equal to 4. So this will be equal to 6 minus 6 times n, which is 4. This will be equal to 6 minus 24, which will be equal to minus 18. Is our T4 equal to minus 18? It is. Good. So do we have confidence that this relationship represents our terms? Yes, we should. We should have. So if I were to ask you in general, what is the 100th term of this sequence? We know that Tn in this case is 6 minus 6n. And where are we getting this from? We're getting it from the general one which we just derived together, a plus n minus 1d. Only that in this case we do have our a, we do have our d, so we can simplify that to get that. So if you want T100, say, how do we find the 100th term? What is n equal to? If you are looking for T100, n equal to 100. Good. So T100 will be equal to 6 minus 6 times 100, which will be equal to 6 minus 600, which will be equal to minus 594. So T100 for this sequence is minus 594. Are we happy? Okay, good. Obviously, the next question that you're going to ask me is, you have said that this type of a sequence is an arithmetic sequence. What are the other types? Okay, that's what we actually want to look at now. Tn is equal to 6 minus 6n for this sequence. Let us take a few examples. Let us take a few terms and try to check if we are actually correct. Easy. Let's start with the first step. Let's see if T1 is for sure equal to 0. So T1, what is n equal to if we talk of T1? Guys, why are you quiet? What is n equal to? What is n equal to when we talk of T1? 1. So this will be the same as 6 minus 6 times 1, because n is equal to 1, which is the same as 6 minus 6, which is equal to 0. Do we agree that our first term is 0?
Yes.
Yes, we should. It is. Let us take another term. Let's take T for fourth term. T. We know that in general, Tn in this case is 6 minus 6n. So T4, my question to you guys, what is n equal to now? 4. Tn, T4, n equal to 4. So this will be equal to 6 minus 6 times n, which is 4. This will be equal to 6 minus 24, which will be equal to minus 18. Is our T4 equal to minus 18? It is. Good. So do we have confidence that this relationship represents our terms? Yes, we should. We should have. So if I were to ask you in general, what is the 100th term of this sequence? We know that Tn in this case is 6 minus 6n. And where are we getting this from? We're getting it from the general one which we just derived together, a plus n minus 1d. Only that in this case we do have our a, we do have our d, so we can simplify that to get that. So if you want t100, say, how do we find the 100th term? What is n equal to? If we are looking for t100, n equal to 100. Good. So t100 will be equal to 6 minus 6 times 100, which will be equal to 6 minus 600, which will be equal to minus 594. So t100 for this sequence is minus 594. Are we happy? Okay, good. Obviously, the next question that you're going to ask me is, you're saying that this type of a sequence is an arithmetic sequence. What are the other types? Okay, that's what we actually want to look at now. Like what I was saying, is obviously because we have actually said that it's only one type of a sequence, there should be others. Alright, at our level, we are going to limit ourselves to 2 only. So the next sequence that I'm actually going to introduce, and we'll discuss that together, and do exactly what we actually did with the arithmetic one, is what we call the geometric sequence. Okay, this is where what I was saying earlier comes into play, the times table. Okay? Let's think of something. Let's say we have this pattern here. 1, 2, 4, 8, 16. What do you think comes after? Look at it very carefully. 32. Good, guys. And after that?
64.
64. And so on. If we're to try and think carefully, it will be very easy for us to see that this is not an arithmetic sequence. How can we see that? Remember, by definition, we say that an arithmetic sequence is where we have a common difference between a term and its predecessor. Right? So if we were to try to check the same thing, Tn plus 1 or Tn minus Tn minus 1 here, you will see that we actually don't have a common difference D. Right? Let's check. T2 minus T1 is 1. Right? Yes. T3 minus T2 is 2. Already, you stop. There's no common difference. If you were to go further, T4 minus T3, 4. So there's no common difference. We are not adding a constant term to get the next one, like what we're doing with the previous sequences. Do we agree? Yes. Correct. What are we doing in this case? Someone clever to tell me. What exactly are we doing? How are we how are we moving from one term to the next? In this case.
Multiplying by 2.
We are multiplying by 2. Ah, good. Very good. We are multiplying by 2. So, if I wanted the term after this one, I would simply multiply this 64 by 2, and I get 128. I want the term after that, I multiply by 2, I get 256. If I want the next one, I multiply by 2, I get 512. If I want the next term after that, multiply that 512 by 2, I get 1024. etc. Multiply by 2, 2048. And continue like that. Agree? So, of course, we do agree now. This is actually a different type of sequence. In the same manner that we saw with the arithmetic sequence, we actually have a starting term. What is our starting term in this case? What is our first term? 1. We agree we use again the first letter of the alphabet, A, for the first term. Happy? How would I say? If I were to label these terms, we still have terms. This would be term T1, T2, T3, T4, T5, T6, T7, right? Until we get to some term Tn. Happy? Good. What would happen if I were to do the following to my sequence? If I were to start adding now or subtracting the terms, do I still have a sequence if I do that? No. What do we call that?
Series.
It's a series. Right? Just like, in fact, taking from where it's coming, right? We also call it a geometric sequence. Sorry, series, if we start adding or subtracting the terms. And in the same manner that we did with the arithmetic sequence, we can also do the same here. We can call it also a geometric progression. If we do that. But we are not going to talk about series and progressions until we finish talking about the sequences from where they're born. So, that was just to mention that in passing. So let's look at our sequence again. We agree A equal to 1. Then someone has told me, very clever, very intelligent, that all we are doing is to multiply a term by 2 to get the next term. Alright? So if you try to look at this, this is what we've actually done. 1 times 2, correct? To get the next, and of course we get 2. To get the next term, we are saying 1 times, which is this now, times 2 again. To get the next term, 1 times 2 times 2 times 2. To get the next term, 1 times 2 times 2 times 2 times 2, and so on. Do you agree?
Yes.
Good. Now, question. From around grade 8, grade 9, we dealt with the laws of indices. Right? We know that. That's what we're actually bringing to this level. That's why they were doing it with you, so that we can actually apply those things here. If I were to ask you, this is the same as 1 times 2 to the power something. What is that something? 0. Why? Because we know that any number raised to the power 0 is 1. Correct?
Yes.
This will be the same as 1 times 2 to the power 1. Correct? This will be the same as 1 times 2 squared to the power 2. 1 times 2 to the power 3. 1 times 2 to the power 4. And we continue, obviously. 1 times 2 to the power 5, 1 times 2 to the power 6, 1 times 2 to the power 7, and so on. Right. If you remember what we did with our arithmetic sequence, we looked at this general relationship and the terms and the term number. Then we could actually went on to find, okay, so what is Tn in general? We can actually do exactly the same. But before we do that, let us ask now, if we're to be given a sequence, a geometric sequence in general, how do we know what we are multiplying terms with? About. That's what we want to find out. And we'll show you just now. That is actually very easy. Let's look. We say we have a common ratio. A common term which is multiplying one term to give us the next. Okay? If we try to look, let's try to check. T2 divided by the term before it, T1. Let's look at T3 divided by the term before it, T2. Let us look at T4 divided by the term before it, T3. Let us look at T7 divided by the term before it, T6. And therefore let us look at Tn in general divided by the term before it, Tn minus 1. And let's try to see what we get. If we look at those, we'll see the following. T2 divided by T1 is actually the same as 2 divided by 1, which is equal to 2. Which is the number that we said we are multiplying everything, by, for us to get the following number, or the following term. If we look at T3 divided by T2, this is the same as 4 divided by 2, which is 2 again. If we look at T4 divided by T2, that's the same as 8 over 4, which is 2 again. If we look at T7, which is 64, divided by T6, which is 32, we get 2 again. So in general, therefore, if we look at Tn in this case, divided by Tn minus 1, we should also get 2. Does that make sense? Yes. You don't sound confident. Yes. Is that a yes? Yes. Okay, good. Now, let us, this which we have seen for this particular sequence, this is the 2 that we're multiplying. So we multiply this by 2, we get that. Multiply by 2, we get that. Multiply by 2, we get that. And we have just seen how to find that common ratio which I mentioned. It's always Tn divided by Tn minus 1. Similar to what we saw. If you want to find a common difference for an arithmetic sequence, it's Tn minus Tn minus 1. In this case, the only difference is that we are multiplying, so to find it, we divide the terms, which is what we've actually done. Divide the terms, and of course you get your common ratio. Now, let us do it now in a general manner. In a very general manner. That common ratio that I've discussed, in this case, which is the 2, which we have said is Tn, so a term divided by the term before it, let's decide to call it R, common ratio. Yes, common ratio, well, let's call it R. Right? So, if we were to have, so now somebody comes and tells you, I have a geometric sequence, the first term is A, my common ratio is R. Can you please write that sequence for me? What would we do? What would be our first term? A. Correct? What would be our next term? If our common ratio, if you're multiplying by R, so what is it going to be? A times R, which is AR. What is our next term? Our third term? AR squared. What is our next term? AR cubed. AR to the 4. Okay? That's fine. I agree with you. Are we all happy at the moment? Good. Now, let us go on to do exactly what we did with the arithmetic sequence. If we try to look at these terms, so that we can actually have a relationship between the term number and this, what are we going to actually do? We are going to say, okay, fine. We see that this is T1, this is T2, this is T3, this is T4, this is T5. If I were to write our subscript n, right? This is T1, so n here is 1.
1.
Here?
2.
2. Here? 3. Here? 5. Let's talk of a term Tn, where n obviously is equal to n. Correct? Good. If that is the case, let us try to see what is happening. There's actually a relationship which I'm going to make you see now. If we try to look at everything, what is the power here of R? 1. What is the power here of r? 0, because r to the power 0 is actually equal to 1. So let's try now to look for a relationship. When my n is equal to 1, here my power is equal to 0. When my n is equal to 2, my power is equal to 1. When my n is equal to 3, that's the third term, my power of r is equal to 2. When my n is equal to 4, my power is equal to 3. When n is equal to 5, fifth term, my power is equal to 4. Now let's ask a simple question. So what about when n is equal to n? Obviously, we have one thing that we can see throughout. We always maintain our a. So we can confidently write that yes, we are supposed to have an a somewhere. The other thing that we have seen is that we are always going to maintain our r. So we can confidently write we are going to have an r. What is it that we've seen, or what is it that we know is actually changing? It's the power. And we've seen from 2 to 1, 3, 2, 5, 4, 4, 3. So what about when we are having n? What are we supposed to have as a power here? N minus 1. Happy? So what are we saying? The nth term in general is a times r to the power n minus 1. That's easy. We can see that. Okay, so let's write that in general. So for a geometric sequence, the nth term Tn is equal to a, the first term, times the common ratio to the power n minus 1. Do you agree? Is that derivation difficult? No. Take that in our notes, and of course I'm sure we've taken the derivation itself. So that obviously as we read our notes in time, this will become second nature. You'll be able to do that anytime. Okay, now let us convince ourselves that what we are saying here is correct. Okay, that's our relationship. Let me write it somewhere in the corner so that for now you can easily refer, but over time that will become part of you. So Tn, as we've seen, is equal to a r n minus 1. Let's try to use that. Let's stick to the sequence that we are having at the moment, where we have agreed that a is equal to 1. Agreed? We have also seen that our common ratio, which we have said is actually in general Tn plus 1 divided by Tn. Take any two terms, take any pair, a term and its predecessor, a term and its predecessor, and do the division. So let's take, for example, T2 divided by T1, that will be 2 divided by 1, which is equal to 2. Do you agree? Is it the same as T5 divided by T4? T5 will be 16 divided by T4, which will be 8, so that's again 2. So we now understand that our common ratio R is equal to 2 for this particular sequence. Do you agree? Good. If we look at our terms, and then we try to talk of the subscript, what term number is it? N. Obviously here n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, etc, etc. If I were to ask you in general, can you tell us the fourth term of this sequence? Very easy. We'll say, we know that for a geometric sequence, Tn is equal to a times r to the power n minus 1. So if I want T4, the fourth term, Tn, T4, it means that n is equal to 4. This will be the same as a r to the 4 minus, remember n equal to 4, so 4 minus 1, which will be the same as a r cubed. Agree? But what is a? 1. So this will be the same as 1 times, what is r? 2 to the power 3, which is equal to 2 to the power 3. That's 2 times 2 times 2, 8. Is our fourth term equal to 8?
Yes.
Yes, correct. So what will be our 10th term? 10th term, all that means is, we know that in general, an nth term is ARn minus 1. So if we want the 10th term, we can see, this means that n equals 10. Right? We know what our A is 1. We know what our common ratio is 2. Then of course n, we've just said n is equal to 10. So that will be that. What is 2 to the power 9? It's 512. I can allow you to use your calculator. Do you have a calculator with you? Can you find for us 2 to the power 9? It should be 512. At this stage, yes, you can use a calculator. You remember what we said last time? Calculators don't think. They're computational tools. In fact, is it 512? Right, so this will be equal to 512. T10. So the poor kid, the one that we talked about earlier, what would he do? He would say, okay, I can do it after all. I can see you're multiplying with 2. So 1, 2, 3, 4, 5, 6, 7 terms. So if I want the 8th one, that would be 64 times 2, which is 128. If I want the 9th one, that would be 128 times 2, which would be 256. If I want the next one, that would be 256 times 2, which would be 512. If I want the next one, that would be 512 times 2, which would be 1024. If I want the next one, that would be 2048 times 2. If I want the next one, that would be 4096. Correct? Multiply by 2. Then of course he comes and says, okay, so you said you wanted T10. T10 would be, let me count the terms. This would be term 1, term 2, term 3, term 4, term 5, term 6, term 7, term 8, term 9, term 10. So I got 10, actually got T10. Then we come back to the poor kid and say, okay, fine. Oh, good. If that is the case, then please find T50 for us. T50. How do we find T50? We know that Tn is ARn minus 1 for a geometric sequence. So T50, we know what our A is. It's actually 1 times our common ratio 2. Our n is 50. So that will be 50 minus 1, which is 49. What is 2 to the power 49? That's a very big number. Sure, your calculator will tell you error. What did you say?
You gave a big number, to about 10 to the power 14.
10 to the power?
It's 5.6.
5.6 times?
10 to the power 14.
10 to the power 14. That will be 250. So you can see how big this actually grows. If you were to compare this to our arithmetic sequence, we could see our arithmetic sequence was very manageable. We even managed to see for one of the cases, T5000 was just equal to 10,000. If you compare now to T50, just 50. Look at that. That's 5,000 terms. 5,000th term is only 10,000 for that arithmetic sequence. A 50th term only is already such a huge number. This is, I mean, I don't know what that looks like some inflation figure in Zimbabwe or something. That's very big. Okay? So that's one characteristic of a geometric sequence. When we say things are increasing geometrically, they're increasing very fast. Okay? Very fast. In any case, you see that it's actually exponential. Something to the power something. So, that's one other thing that we've learned so far. Let us look at another. Okay, before we probably look at another sequence, just in the same manner that we did with the arithmetic sequence, we said that once we've defined our A and our D, then we can find a unique relationship between an nth term and the A and the D. Equally here, once we define our A and our R, then we should be able to find Tn unique to that sequence. Let's try to do that for this particular sequence, and you'll see how easy it is. For this particular sequence, if we try to think about it hard, we'll see that we have agreed that A is equal to 1, We have also agreed that the common ratio is equal to 2. Are we happy? Good. If that is the case, then if we are going to go back to what we derived on our own, and we should be proud of it, we are not looking at a formula book somewhere, we could derive this straight from a basic consideration. Right? Tn is equal to a r to the n minus 1. Right? Now that we know our a and we know our r, then it should be easy for us to find Tn unique to this sequence. So Tn is going to be a, which we know is 1, times r, but we know that r is equal to 2, then n minus 1. We don't know n. 1 times 2 to the power n minus 1 is exactly the same as 2 to the power n minus 1. So for this particular sequence, the terms will be defined by that. That's the relationship. So if I were to ask you now in general, find for us T5. T5, n equal to 5, therefore T5 is going to be equal to 2, n equal to 5, so 5 minus 1, which is equal to 2 to the power 4, which is equal to 16. Is T5 equal to 16? Yes, it is. Okay, so we can uniquely define a general term of the sequence once we have actually found the first term and the common ratio. Okay, let us look at another sequence, a geometric one. Sorry about that. Let us look at a geometric sequence again. One, 10, 100. What comes next?
1,000.
1,000. Good. What comes next?
10,000.
10,000. And so on. Correct? First and foremost, clever people like yourself, if you're to be given this sequence and nobody tells you that it's actually geometric, one thing that you dismiss almost immediately is it being an arithmetic sequence. Because you can see, these things are growing so fast, there's no way I move from 1 to 10 with a common difference, with a difference of 9. Then from 10 to 8 to 100, already 90. So there's no common difference here, there's no D to actually talk about. So I would not even waste my time looking at that, I'll probably think of a geometric sequence. Now, once we do that, then we have to check and confirm. First and foremost, do you agree that we have a starting term, a first term? What is our first term?
1.
A equal to?
1.
Correct. Okay. If that is the case, how do we look for our common ratio? Tn plus 1 divided by Tn. So a term divided by its predecessor, by the term before it. So if I were to check, I would say, okay, fine, let's check R. In general, should be Tn over Tn plus, over Tn minus 1 if you want. So I can take, for example, T2 divided by T1. That will be 10 over 1, which is equal to 10. I can take T3 divided by T2, which will be 100 divided by 10, which is also equal to 10. I can take T4 divided by T3, which will be 1000 divided by 100, which is equal to 10. So we do agree, therefore, that we have, in this case, a common ratio 10. Okay, if that is the case, then uniquely for this particular sequence, we can say the following. After all, our derivation of the common term, of a term, n or Tn, was for a general geometric sequence. So we can apply it, anywhere. Right? We know that for a geometric sequence, Tn is equal to a Rn minus 1. We're still happy with that? What is a in this case? 1. What is R?
10.
So in this particular case, our Tn is equal to 10, n minus 1. So if I want to find any term, it will be 10 times n minus 1. So if I would ask you, using this unique relationship for this sequence, can you find T1? T1 will be equal to 10. What is n equal to? 1 minus, would you be equal to 10 to the power 0? What is 10 to the power 0 equal to? 1. Because any number to the power 0 is equal to 1. If I would ask you to find the fourth term, T4, what is n equal to? 4. So that will be equal to 10, 4 minus, which is 10 to the power 3, which is the same as 10 times 10 times 10, which is equal to 1000. Is our fourth term equal to 1000? Yes, correct. So in general, I can actually come and ask you, okay, so what is T50? T50 will be 10, 50 minus 1, 10 to the power 49. You can imagine, that's a very huge number. Again, that characteristic of geometric sequences growing very fast is evident, here. But you'll notice, it's not in all cases where our sequence has to grow very fast. It can actually decrease very fast. Let's take a look at an example. Let's suppose we have the following sequence, and I want one of you, because you guys are clever now, to tell me exactly what's happening with this sequence that I'm going to put down here. Let's say I have 2, right? 2 over 3, right? 2 over 9, 2 over 27, and so on and so on. What kind of a sequence is that? Obviously you tell me, I don't know, or we don't know. We have to investigate, isn't it? Do we agree that, like with any other sequence, we've got a first term?
Yes.
What is our first term?
2.
A equal to 2. Happy? Do we also agree that if for sure that is a sequence, then this would be term 1, this would be term 2, this would be term 3, this would be term 4, and we can continue to any term that we want, Tn. Do you agree with that?
Yes.
Now if we do, we could check, do we have a common difference? How would we do that? We would simply say Tn minus 1, and we'll probably take a look at the number of pairs and see if for sure we're actually having a common difference. But I'll tell you not to for now. I'll tell you that it's actually a geometric sequence. So let's investigate if for sure it's a geometric sequence. And then, because I've said it's a geometric sequence and for sure it is, we should therefore have a common ratio and not a common difference. How do we find a common ratio?
Tn plus 1.
Tn divided by Tn minus 1. So we take a term divided by the term before it, we should get that ratio. Then we take, obviously for us to confirm, we'll probably take about 3 or so pairs and check if for sure we're having that common ratio. If that ratio, that division actually gives us a common quotient. Alright? So let's start. The easiest one will be take T2 divided by T1. So T2 divided by T1, this is the same as 2 over 3 divided by 2, which is the same as, you know how to divide numbers, which is the same as 2 over 3 multiplied by, invert, 1 over 2. So that is 1/3. But while that is necessary to do, it's not sufficient for us now to conclude that we have a common ratio. We still have to go on and check with a number of other pairs, is that consistent? Once we establish that consistency, then of course, we can say, look guys, we're having a common, we're actually having a geometric sequence here, the first term is actually 2, the common ratio is actually equal to 1 over 3. So let's look for another pair. Let's take T3 and T2. T3 and T2, that will be the same as, So T3 divided by T2 will be the same as what? 2 over 9 divided by what?
2 over 3.
2 over 3, which is equal to 2 over 9 times 3 over 2. Obviously, that's common, it goes. 3 into 3, 1. 3 into 9, 3. So we end up again with 1 over 3. Let's do one more, just for confirmation. We take T4 and T3, right? So T4 divided by T3 will be equal to 2 over 27 divided by 2 over 9, which is the same as 2 over 27 times 9 over 2. 9 into 9, 1. 9 into 27, 3. So again, we get that common ratio. So we are now confident that what we are having here is a geometric sequence. We are now confident that we are not sitting with an arithmetic sequence. Happy? So we can confidently right now remove all this and write the following. That our geometric sequence has got a first term equal to 2. It has got a common ratio equal to 1 over 3. Correct? So all I'm doing is I'm starting with 2. To get the next term I multiply by 1 over 3. To get the next term I multiply by 1 over 3 and continue like that. Let's see if that is true. We started with 2. We are saying the next term is 2 times 1 over 3. 2 times 1 over 3 is obviously 2/3.
Yes.
We come there, we now have 2/3. To move there, it's 2/3 now. Multiply by the same ratio. We get 2 over 3 times 1 over 3, 2 over 9. To move on, 2 over 9 times 1 over 3 again, 2 over 27. To move on, 2 over 27 times 1 over 3. That will be equal to 2 over 81, and so on and so on. Now, like we have done with all the other sequences, let us try to find a unique relationship between the nth term and n. We know that in this case a is equal to 2, r is equal to 1 over 3. Alright? More importantly, we also know that because it's actually a geometric sequence, the nth term in general is a Rn minus 1. Is that correct? We have just seen that. So now that we understand that a is equal to 2 and r is actually equal to 1 over 3, we can write this uniquely. So Tn for this particular sequence will be equal to a, which is 2, times r. What is r? To the power? N minus 1. So uniquely, what does that mean? It means that this is how we actually get, this is generally how these terms are actually related to each other. So if we want to find, for example, find for us the fifth term. We've just seen that the fifth term, T5, is 2 over 81. Because we say this, it will be T4 times 1 over 3. So if you want to find the fifth term, T5, n equal to 5. So it will be equal to 2 by 1 over 3 by n, which is 5 minus 1. So that will be to the power 4. Obviously, this will be the same as 2 times 1 over 3 to the power 4. 1 over 3 to the power 4 is exactly the same as 1 over 3 times 1 over 3 times 1 over 3 times 1 over 3. Okay? So this will be the same as 2, remember, times all the ones, divided by 3 times 3, 9, times 3, times 3, as we said. So then we can confidently say, yes, this is what actually describes. This is the relationship between an nth term for this particular sequence and the term itself. Sorry, I mean, anyway, now that we are this far, let us let us discuss something very much, investigate these sequences. Let's start with the geometric ones in greater detail and define a few things. Initially we looked at the sequence 1, 2, 4, 8, 16, 32 and so on, and we saw the relationship between Tn and n, easily found it. And now we've just gone on to look at this sequence 2, 2 over 3, 2 over 9, 2 over 27, 2 over 81. Obviously this one will be 2 over 243. So the next term, and so on and so on. I want us to notice something. Let's go with this sequence 1. We said in this particular case, our A was equal to 1, our R was equal to 2. I want to ask you, what do you think would happen to these numbers if we continued with the terms? Would they continue growing bigger and bigger and bigger and bigger?
Yes.
Are you confident?
Yes.
Yes. In fact, we saw that. We saw someone telling us just now that the fifth term was what? 2 to something 5.6 times 10 to the power 14. Very big. So as we increase n, with n increasing, we will actually discover that as it becomes bigger and bigger and bigger, our terms are going to approach. They will not be equal to plus infinity. There's nothing equal to plus infinity. They will approach a very huge value. They will approach very huge numbers. Plus infinity will approach that. They'll become bigger and bigger and bigger. We just talked about that inflation figure. 5.6 and 10 to the power 14. That's a very huge figure. Okay? And we saw that with this particular sequence. Now the tricky part comes here, is actually here. Let's investigate the second case and see. Then we can say what I want to tell you. We have just seen that A is equal to 2. We have also seen that R is equal to 1 over 3. If we look at our terms, these are actually fractions. Do you agree?
Yes.
They are. Most of them. Maybe save for the first term, which is, a whole number. After that, we're talking of fractions and fractions and fractions. What do you think is going to happen as n increases? If we continue adding, if we continue putting terms, let's say now I talk of T50. What do you think is going to take place? If you try to check, we started with 2. The next term was already 2/3. Next term 2 over 9. 2/3 is smaller than 2. 2 over 9 is smaller than 2/3. 2 over 27 is smaller than 2 over 9. So eventually, if we were to continue adding this, where do you think we'd actually end? Yes, not adding, if we were to continue putting terms. Negative? Do you see anything which looks like negative here?
No.
What do you think would happen?
The value of the term will be decreasing.
The value of the term will be decreasing. Until what happens? What do you think is going to happen? We are going to approach 0. How do we know that? It's basic. If I have a number, A, which is fixed, you can see that. Like here, our A will be our 2, fixed. And I've got a number, B, which will be dividing A. That's the simple property of division. If I'm going to divide something by a very large number, I'll make it smaller and smaller and smaller and smaller. If I make this infinitely large, this is going to approach 0. So there will come in this particular case some terms where we have actually approached 0. We are essentially now at 0. So after such, we say that if Tn is actually 0, then Tn plus 1 should be 0 as well. Because obviously in that case, the same denominator or the same divisor which is making this to be 0 will be bigger. So after that, we actually approach 0. In fact, everything else now tends to 0. Tn plus 1, 0. Tn plus 2, 0. Tn plus 3, 0. Are we happy? Yes. Moini? We are happy. So we take down in our notes such a case where we end up with our terms approaching 0, which means they are not changing anymore. We say that our sequence essentially converges. What is to converge? When we say something converges, we say we are effectively saying if we are going to start different, we will meet somewhere and nothing changes thereafter. Okay? So such a sequence converges. We say it is convergent. We will investigate the conditions which are necessary and sufficient for a sequence to converge. Just now. Let us look at the first case. 1, 2, 4, 6, 8. You rightfully say it to me. If we are going to continue putting terms, such terms eventually are going to approach plus infinity. Right? So we'll never come to some common term. To that 0, where we don't have terms, changing, anymore. It will continue to increase. I'm now at 1 billion. The next thing I still have to multiply that 1 billion by 2. The next thing I have to multiply that again by 2. And continue becoming bigger and bigger and bigger. And going further and further and further, off wider and wider and wider and wider. We say that such a sequence is divergent. Divergence, and we have seen also convergence. I will say without proof, although I'm going to explain why. In fact, we can actually say it with proof. With proof. What are the conditions necessary for us to have a sequence converging? I'll give you the condition. It's only one. That condition is that the common ratio has to be a number which lies between -1, less than -1, and less than 1. So it has to be a fraction. So our common ratio has to be that. What is the proof? I'll give you the proof now. Okay? What do we mean when we say our common ratio is less, when we say our common ratio is less than 1 and greater than -1? This is what we mean. Let us look at the number line again and think about it carefully. If we look at the number line, we say if this is 0, that's 1, that's 2, that's -1, that's -2, and we can continue. Right? If we try to think carefully what this statement, what this inequality, this enclosed inequality really means, it is the following. We are saying that R has to lie in which region? Only here. This not included, that not included, but only there. Let's ask ourselves what that means. Yes.
You said R.
Yes.
It has to be greater than 1. but
It
less
has to be
than-
greater than minus 1,
Okay.
but less than 1. So it has to lie within this region. What does that mean? In the region where we are having, in this region, if you really try to look at what numbers do I have between 0 and 1? What kind of numbers? Think of any. Think of any number, half, 0.5. Half. Another one? Think of another number. Quarter. Another one? 0.3. A fifth. What else?
Minus half.
Here, minus half. What else? 1/3. Minus 1/3. 1/3 here. Take a look at those fractions. They are proper fractions. Effectively, we can write that. If we really wanted to consider this inequality, this means that the modulus of R should be less than 1. What do we mean by modulus? The absolute value. Did I say the right thing there? Should actually be less than 1. What does that mean? The modulus of minus 2 as an example. If I talk of that, we are saying what is the okay. If we look at that as a quantity, this will be actually equal to 2. We just want the absolute value. We are not worried about the sign. So if we say modulus of R is actually less than minus 1, so it's actually less than 1. What does it mean? If it means that, for example, if R is equal to minus 2, modulus of R is equal to 2, which means that in that case, such a sequence has to diverge, because obviously 2 is not less than 1. What cases then are we going to have where this is going to be respected? It is all these fractional cases, and they have to be simple fractions, with the denominator being bigger than the numerator, so that you are lying between minus 1 and 1. Then we are talking of a converging sequence. How can we prove that? We can prove that very easily. Let's go back to what we said. We said that the nth term of a geometric sequence, Tn, is equal to A, right, times R to the power n minus 1. Are we happy? Good. Now, okay, if that is the case, let us just ask ourselves what exactly we are saying here. What we are saying is, let's make this a fraction, right? Make it a fraction in such a manner that, how can you write a fraction, I mean, in general? Probably x over y. And we are saying that this fraction, x over y, has to be less than 1. Absolute value. This actually gives the fundamental proof that for us to converge, our common ratio has to be a fraction, and a simple fraction. Okay? We have said, we understand that the nth term for a geometric sequence is actually A, first term, common ratio to the power n minus 1. And we have just said, if you're going to have a simple fraction, x over y, as your common ratio, right? A simple fraction simply means that the denominator is bigger than the numerator. So it's obviously something which is less than 1, or minus 1, or bigger than minus 1. As we've said, it's lying in this region. 0, 1, minus 1, but not including the 1 and the minus 1. Alright? So it's a simple fraction, something like minus 1 over 3, minus 2 over 3, minus 1 or 5 over 8. That's a simple fraction. That fraction is less than 1. We can see that. So suppose we have x and y such that x is less than y, then obviously our fraction becomes a simple fraction, like what we're actually talking about here. Or if, let's talk of the absolute value, because, for example, if I have minus 1 over 3, yeah, it's still the same, I mean, actually. Because my x, if I look at the absolute value of x, it's still going to be less than y. So it's actually a simple fraction. Now, if we say that, then we say Tn, therefore, looking at that, will be equal to a times r, but we're saying that our r, in this case, is this very simple fraction, x over y, to the power n minus 1. Let us see what's going to happen. Is it going to converge? How do we know? We'll say, okay, fine. Therefore, this means this is exactly the same as Tn, okay, as n becomes big, as n approaches plus infinity, as n becomes bigger and bigger and bigger and bigger, then we can safely say that, I'll introduce this, we'll talk about it in other sessions, the limit as n approaches infinity, we'll discuss this when we do functions later, the whole aspect of limit, will be equal to, can you see that? A, or the limit, is n approaches infinity of a, which we know, x over y, limit of that. But now let's check. Let us check something. If y is bigger than x, what are we having? We are saying that it is going to grow much, much faster than x. So effectively, we are now having a fraction where our denominator is becoming bigger and bigger and bigger and bigger and faster than that. So eventually, this term approaches 0. It does. If it approaches 0, then this limit, it will be a times this, which is actually approaching 0. So a times 0. Therefore, Tn, for that limit, as we approach infinity, Tn is going to approach 0. However, suppose now x is bigger than y. What would happen? It would mean that this x is going to grow much, much faster, much, much bigger than y. So we are going to end up with a real number, big number, to some power, which will never approach 0. That's when we actually end up diverging. If that's actually difficult to look at, you actually don't have to memorize that. It's okay. They will never ask you a question like prove that if, or what are the conditions when we actually really need convergence and therefore prove it. All we simply need to know here is that our r has to be a simple fraction for us to converge. If we look at a general term, if r is a number which is bigger than 1, let's say 2, or even equal to 1, by the way, what's going to happen is a, let's take an example of 2, will be equal to 2, n minus 1. As n becomes bigger and bigger, obviously 2 to the power something is also going to become much bigger, bigger, even. Correct? So, we will not converge there. We will actually diverge. That's what we simply wanted to say. Right? Let's finalize the aspect of sequences by agreeing on something. I'm going to tweak your brain a bit and you answer me. We looked at an arithmetic sequence and we say we have got a plus d, a plus 2d, a plus 3d, etc. For a common, we have got a first term, then we add the common difference. Do you think it is possible for a sequence, for an arithmetic sequence, to have its first term being equal to 0? Is that possible? It is. So we can actually start with 0, 2 if you want, 4, 6, 8, 10. That's the sequence. Are we happy with that? Equally. Let's look at the following. Is it possible for an arithmetic sequence to have a common difference which is equal to 1? Yes. So we can start, say, like in this case, it's 0, 1, 2, 3. Our first term is 0. Our common difference is 1. We're adding 1 subsequently. Happy? Let's ask ourselves the same questions with a geometric sequence. A geometric sequence, we said, the first term is A. The second term is AR. We multiply by that common ratio. The next term is AR squared. The nth term is ARN to the power, sorry, is actually AR to the power n minus 1. Do you think it is possible for a geometric sequence to have A equal to 0? No.
No.
Someone says no? We say no. Of course it is not. If I start with a term, with my first term being equal to 0, no matter what the common ratio is going to be, if I multiply 0 by that common ratio, I'm going to end up with 0. If I multiply by that again, I'm going to end up with 0. So I cannot have a geometric sequence starting with the term 0. Is that easy to see?
Yes.
Good. 2, do you think it is possible for us to have a geometric sequence where the common ratio is equal to 1?
No.
No. Why? Because if that becomes the case,
It's an arithmetic.
we got a problem.
Yes.
Because if our A is A, right? And then we multiply by 1, we've got A. We multiply by 1, we've got A. We multiply by 1, we've got A. It's effectively an arithmetic sequence. What will be the common difference there? 0. Correct. So we have seen now that the requirements for a geometric sequence are a bit more stringent. While we can actually have a first term equal to 0 for an arithmetic sequence, it's not possible to have A equal to 0 for a geometric one. While we can have a common difference equal to 1, it's also not possible to have a common ratio equal to 1. Good. Now finally, to conclude this, we still have a bit of time to go. To conclude this, we want now to look at, we've seen these terms. What happens if we were to add or subtract these terms? We said once we start adding terms, we are now sitting with a series. So we are going to look at the series in 10. Right? We'll start firstly with an arithmetic sequence. Sorry, with an arithmetic series, also known as an arithmetic progression. The only difference between this and the sequence, and the sequences that we saw, is that in this case we are going to be having some operation of some sort. We are going to either add the terms or subtract them. So, remember the first sequence that we actually started with was 1, 2, 3, 4, 5, 6. This is the interesting part earlier. So be attentive here, because that's what they're actually going to be asking you later. That's the sequence. Agree? What is the first term of this sequence? 1. What is the common difference? 1. If I were to do the following, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus some term in plus some term n. What I've just created there is an arithmetic progression. It's an arithmetic series. Because I am adding the terms of an arithmetic sequence. Right? The question that we want to ask ourselves is it possible for us to deal with this? Is it possible for us to find such a sum? In the same manner that we actually found some relationships between terms and n, Tn equal to this, Tn equal to a plus n minus 1d, can we also do exactly the same or something similar for us to find such a sum? I'm going now to introduce what we call the sum of a series. Sum of a series, sum. We will represent that with the letter S. And in the same manner that we're using subscripts for terms, we are also going to do the same for the sum. As an example. So, if we were to come to you and say, find S1. Listen carefully, because if you get that right, then we'll never have a problem. And we can conclude this lesson very well. If we say S1, we are saying what is the sum of the first term. Obviously, it's just one term. It will be 1, this term, here. If we say S2, we are saying what is the sum of the first two terms. 1 plus 2, which is equal to 3. If we say S3, we are saying what is the sum of the first three terms. 1 plus 2 plus 3, which is equal to 6. If we say S5, we are saying what is the sum of the first 5 terms, which is equal to 1 plus 2 plus 3 plus 4 plus 5, which is equal to, what is it equal to? 15. Correct. So if we say then in general, what is Sn? We are saying what is the sum of the first n terms, beginning with your first term, beginning with A. So you add from A, you go to the next term. So we actually add T1, T2, T3, T4 until we get to Tn. Add everything, what do we get? I know we are tired now, but we have to finish. So let's actually just do that quickly and establish a few things. If we look again at our arithmetic sequence, and now we are going to turn it into an arithmetic progression, into an arithmetic series. We say that in general, if we start with an arithmetic sequence with the first term A and a common difference D, then it means that our first term is A, our second term will be A plus that common difference. Our third term will be A plus 2 times the common difference. So it's actually A plus D plus D. Our fourth term will be A plus 3D. Our fourth term will be A. That's our fifth term will be A plus 4D. Do you agree with that?
Yes.
Correct. That we know. So, if we really want to ask ourselves a simple question, remember, this is T1,
Yes.
this is T2, this is T3, this is T4, this is T5, and we can continue to some Tn of some sort, any that we can think of. Now let's talk of the sum. Then we can actually establish the relationship between the term number and the sum. Right? If we ask ourselves, what is S1? Looking at our generalized arithmetic, series. Right? If you're going to be adding this now, what is the sum of the first, that's the first term on this one? So S1 obviously is going to be equal to A. Do you agree, Anya?
Yes.
That's this first term. What will be S2?
2 plus
2A, what is it? 2A plus?
D.
2A plus D. T1 plus T2 will be A plus A, which is 2A plus D. What is S3? It's A plus D plus A plus 2D. If we check, it's A plus A plus A plus D plus 2D. 3D. Is that correct? What will be S4? It will be T1 plus T2 plus T3 plus T4. So that will be A plus A plus A plus A plus D plus 2D plus 3D. Is that correct? So that's 3 plus 2 plus 1 plus 6D. Correct? Now, boys and girls, ladies and gentlemen, here is my simple question to you. What is Sn then? I want you to look at the pattern that I've actually generated and tell me something. How are we getting these terms? Check. S1, 1A. S2. Okay, let's deal with the A first. Alright? S1, 1A. Remember, n equal to 1 here. N equal to 2 here. N equal to 3 here. N equal to 4 here. N equal to n in this particular case. Alright? So let's look carefully. S1, 1A. S2, 2A. That's just considering the A's. S3, 3A. S4, 4A. S5, 5A. S6, SN, NA. Do you think the A's are sorted?
Yes.
Well, I think so too. They are sorted. Yes. But if you notice, let's look at here. What is our D here? 0D. Let us ask ourselves a simple question. How do you think we are getting these D's from here? We've just seen, in the case of A's, it's very easy. 1A, 2A, 3A, 4A, and A. But what do you think is actually happening with D? Sorry, with our D's. Let's forget about the 0 one. It will confuse you. It's not there after all. Let's talk about these 3. How do you think we're actually getting them? From 2, 3, 4.
It's n minus 1 times d. No, it's no, I'm lying. No.
It's not n minus 1 times d.
No.
How do you think we're actually getting them? Anyone who can see? Anyone who can see how we are getting those from here?
It's 2n minus 1.
2n minus 1. That's a good guess.
It's something to do.
If you really notice, take a look. Take a look. Right? What are we doing? This is what we're actually doing. As we move to S2, which is our true first sum, really. Because S1 we are basically talking of the first term, is not actually added to anything. When we really start doing the addition, if you look at S2, if you look at that, we're getting 1. Don't you think all that we have done here is to look at S2 and S1, 2 and 1s, so 1 times 2 divided by 2. Yes, this 2 times 1, we divide by 2, we get 1. Do you get that? Yes. Why are we confident to say that? Because we can actually see the pattern. Let's look at here. We have got 3D. If you look at exactly the same thing, if you look at, this is S3, if you look at the term before it, remember what we did here? We took the S2 and the term before. We do exactly the same. We take this term and the term before, so 3 times 2 divided by 2, we actually end up with 3, which is this 3D. If we do the same for S4, we end up with 4 times the one before, 3 divided by 2, 12 divided by 2, 6. We get 6D again. So don't you think we're actually having a pattern? So we can actually predict what it is. If we're to talk in general now, let's ask ourselves a question. If we talk of Sn, what was the sum before that? It's obviously Sn minus 1. So equally, we can say that to find this, it will be n times the